Thank you for coming to see my presentation. I will be talking about deep neural networks in social media content analysis, especially multimedia, where the deep neural networks excel at. So let's start. Okay, so why would we even want to analyze social media content? Well, I don't know about you, but for example, I don't watch TV that much, and so it happens more and often to me that when I hear about some news that's happening, it's from social media, and it's actually a main source of information for more and more people. And it's not only about news, but I don't know, there's everything. Social media are becoming like a smaller internet where you can find everything. And there is this incredible amount of data that we can analyze. We have information about, we have many videos we have information about how many people watched them, how they reacted to them. And we can use this data to analyze what users like, what users want to see, what users pay attention to. And especially with videos, we can see that in social media sites like Facebook, they tend to go more viral and have more views, even if it's just I don't know, a recipe. It can get over 300 million views. And we can perform this kind of analysis that will be useful for publishers, like to make videos about what users respond to better. So there's a good business value here. And today I will be talking about 3 applications: logo detection, text extraction, and popularity prediction. So let's start with logo detection. So first, why would we want to be doing such analysis? Well, if you're a brand owner, you might want to know in what context your brand is visible. So if, for example, it is not a factory of cocaine in your factory of Coca-Cola, you want how much your logo is exposed, in what context it is seen, is it positive or negative sentiment, and maybe where should brand owners invest when they sponsor some events, how much this brand is really visible. So I think, it's worth investigating. So this is what our assumptions were. We shouldn't need a lot of data because nobody wants to spend time annotating it. Our solution should be able to detect even small logotypes because that's how they often appear, and should be fast because we want to apply this analysis on videos. We need to often apply detection frame by frame. So for this, we used a Flickr dataset that consists of 32 classes, has about 40 images per class, so it's not a lot for deep learning approaches, about 4,000 background images, and we implemented our solutions in Keras with TensorFlow. Okay, so how can we tackle this problem? A traditional approach would be to train a classifier that is able to distinguish image of a logotype or a background for a fixed size image, and apply a sliding window to crop, to provide with all the possible locations where the image can appear. But of course, this is very, very inefficient because we need to consider all the possible locations, all the aspect ratios or the scales, and this would be just impractical to apply in practice. So a solution for this, we can actually perform this with convolutional neural networks much more efficiently. Usually in deep neural networks, applied to image, you have a lot of convolutional layers, pooling layers, and in the end, you have a fully connected layers that take fixed input size and output a fixed size output. So that's why if you use fully connected layers, we need a fixed input size image that would produce that will produce appropriate input for a fully connected layer. But actually, we can replace these fully connected layers with convolutional layers that will do exactly the same thing. Will be applied to the feature map of the size that was produced. And this way, we can run these convolutional operations on the image of different sizes and produce feature output map with scores for different logos that we want to detect. And in Keras, this is pretty simple. In case of convolution on fully connected layers, we have this dense layers, and we can just replace them with convolutional layers that have filter size of size that was the output of the previous layer. We also have to apply softmax in this 4-dimensional because we get this spatial scores. So yeah, this is exactly what it looks like. In training time, we still train for the fixed size images. But at this time, because we have these convolutional layers at the end, we can run it on image on any size. And as a result, we will have just a bigger output that will provide us with scores for different classes, but in different locations. That's a good way for efficient sliding window implementation with convolutional neural networks. So, because we didn't want to have a lot of data, what we also do is we use data augmentation. And for that, for background images, we just take random crops of background images that we have that contain no logos. For logo images, the way we do it, we take random crops of logos that have this intersection over union, so just this common area of above 0.5. And this is an example of how it works. And this is done online. We don't compute these images and store it beforehand. Just when these images are needed for training, for another iteration of training, they are generated in Keras. It's just a simple Python generator that can do that. So thanks to that, it's very unlikely for the network to see exactly the same example more than once. Okay, so our first attempt was to use exactly what I just said, just use the fully convolutional neural network. Because we didn't have a lot of data, of course, we started with fine-tuning fully neural network that was trained on ImageNet. We chose the ResNet architecture, modified it to use only convolutions, so it's fully convolutional, as I said, trained it on the fixed input, used data augmentation, applied minimized cross-entropy loss as our objective function, and we got this. So this is not exactly what we wanted, because we wanted a very precise location. But although the classification is good, the location is not what we wanted. And this might be partly because of this data augmentation that we needed because we didn't have a lot of data. But it could have introduced some problems with localization. So our solution for that is introducing bounding box regression. And the way this is done is so the part on the left is a common part of convolutional neural network that produces some feature maps. On the top, we have this classification head, which was also something that was done before. And now we add this regression head that also, based on the output of intermediate layers of convolutional neural networks, provides 4 numbers that correct these bounding boxes that would be produced by just classification for a given image. And for that, we also needed to update our data augmentation to provide not only with the images augmented, but also these 4 numbers that are able to then correct the precise location the bounding box that will be produced. So, yeah. But it still wasn't enough, because if we use fully convolutional ResNets, this is a very big network with many parameters, with big input size, it was 197 per 197. So if you want to detect small logos that are like 10% of an image, we would need to resize it first to 2000 by 2000 pixels, and it would be even slower. So it turned out to be quite impractical as well. And we came up with another solution for that. We used a cascade of networks. So in this case, first we train a smaller neural network that only provides with proposals of where the logotype may appear. So it's a small network with only a couple of layers, not that many parameters, that will be not very precise, but will limit the possible locations of where the logotype might appear. And we'll do it quickly, because it's a small network with smaller input size. Then, with the output of this first network, we refine these proposals with ResNet that is trained similarly to before, but is now only evaluated on fixed input size. And this time we can evaluate it providing batches of images, which will be also much faster. And this ResNet is able to discriminate the proposals from the background and proper logotypes. And also this ResNet, in this case, is trained with hard negatives, that is negative proposals that had a high confidence score. So it even more improves discriminability of this network. And this is an example of like a real example, where on the left we see the output of our proposal network that's predicted where a logotype might appear. And on the right, this is after our second, more powerful network refined it. Okay, so this is it for logo detection. Now let's move to text extraction. And again, why would we want to do that? Well, it appears that many videos now, especially on Facebook, are designed to be watched on mute, but with subtitles. And this is because, as I read recently, that 85% of Facebook videos are watched on mute. So the publishers, they chose to create videos this way, so that you can still enjoy them, I don't know, consume them when you're on the bus, on the subway, and get the entire information. And actually this, what makes it interesting to extract this text, because these subtitles often define the story about what is happening in the video. So if we could have access to this text, we could further analyze it with using NLP techniques, know what the video was about, how users reacted to different tags, different stories, different categories. Okay, so text extraction would consist of two steps: text detection and text recognition. In our experiments, we used, after initial experiments, we used text boxes as for text detection, which detects where in the image words are located, and text recognition, which takes the image of a word and outputs a string what the word is. So those two work together quite well. So a couple of words how text boxes work. I don't want to go into very much details, but they are based on SSD object detector called a single shot detector, and they perform classification on outputs of intermediate feature maps that have different spatial resolution. And thanks to that, with just one forward pass, they can predict where they can detect the text on multiple scales and locations with just one pass through the network. And this is the SSDs was done for object detection, and this is an approach that is adjusted for text for this more horizontal, that has more horizontal aspect ratio. And yeah, and models for this are available. This was implemented by the authors in Caffe, and this is so we need to write a Python wrapper to use it in our projects, which is quite easy. We can initialize the network with the provided models. I usually like to wrap it in a single class that can do it all. We define a transformation that will resize to the input that this model requires, transform the image, and do a forward pass with the image, the data. Okay, and these are some examples from the publication of how it works. You can see that it can detect words quite well. The red bounding boxes are false positives that appear sometimes if there are some images that resemble characters. But in general, it works quite good. For the text recognition, we are using CRNN, which are convolutional recurrent neural networks that are able to recognize single words, and with the PyTorch implementation. The way they work, they apply convolutional layers to the image, and after several layers, these feature maps are split as feature sequences and fed to recurrent neural network that then produces the predictions of what word it is. And we can just put it all together, use our text boxes for detection that is implemented in Caffe. We can use our CRNN recognizer that is implemented in PyTorch, and that way get the results that you want. For example, detect texts, crop the words, and run it through the recognizer. Would Wonder Woman beat Thor's ass? I don't know. Text extraction, okay, examples, yeah. And these are some examples on our data. Yeah, it seems to work quite okay. And now we move to popularity prediction. So the question is, can we predict popularity of a video from its visual features? And well, we have a lot of data. We have a video. We have information of how they were consumed, how many people watched them, and based on this data, we can try to predict whether the video will be popular just using a thumbnail or first seconds of the video, where often users make a decision whether they are engaged or not. And apart from this analysis, we can make some. We can draw some conclusions of what users like, what kind of compositions, what kind of topics are attractive to users. And this might be important information for publishers as well, how to create these videos, maybe how to select a thumbnail, what users respond to. And the way we approached it, we had a data set of about 37,000 Facebook videos that were published in a span of 3 months. And online for at least 2 weeks, so that we know that the number of views is more or less settled. And we can use thumbnails or first seconds of the video, because that's actually how the way Facebook counts views is whether user watched it after, I think, 3 seconds. So we all need to prepare the data. We treat popularity we determine if the video is popular by using number of views. We need to normalize this data because, of course, different videos are posted on different pages that have different number of likes. So there is an advantage for videos that have for videos that were posted on popular fan pages. So we normalize that number of views by the number of likes on the fan page. This problem can be seen as a regression or classification, but it's much easier to solve as a classification. So the way we did it, we just split the videos and labeled them as popular or unpopular based on whether the number of views is below or above the median value of views. And to train a model like that, we fine-tuned, again, convolutional neural network that was trained on ImageNet. We used the ResNet 50 network that is easily applicable from Keras. And this is just a couple of lines of code how easily we can do it. We initiate the ResNet object with weights from ImageNet. We set include top to false, which means that it won't return out this ImageNet 1000 classes, but will just the features that we can train the network on. We can freeze the layers that were before, and we should do that if we don't have enough data, because if we don't, our network will probably overfit quite quickly. And just add this last fully connected layer that will provide us with predictions. In our case, it would be output two scores for whether the image is popular or not. And these are some examples of best 100 videos that our algorithm found that are most popular, that were not in the training set, and the worst 100 videos. And as we can see, the most popular were videos with food. And we can also see that all of these videos have warmer colors. And on the other hand, the worst 100 videos seem to be more about politics. These are some kind of interviews, and the colors are colder. It's an interesting observation. Another very interesting thing that we can do is try to visualize what parts of image contribute to popularity score. So here we have 4 examples. On the left we have the raw image. In the middle we have a heat map of what part of image contributed to popularity, and on the right we have a heat map what part of image contributed to the score that it's unpopular. And we can see, for example, in here that nudity, of course, makes the video more popular, which is not that surprising, but it's also some kind of validation that this model learned something useful. And stuff like just some text wouldn't generate many clicks. Okay, so in conclusions, I talked about logo detection, for which we can use fully convolutional neural networks and cascade of networks to make it faster. I talked about text extraction, where I showed how we can use detection and recognition to extract text from videos, and popularity prediction, which shows a way to train a classifier that is able to predict whether the video is popular or not, and visualize how it made its decision. And if you're interested in topics like that, we are hiring, and you can check out our websites or drop me an email. And thank you.